Alright, so you see so as we have just now seen, we have these examples of quasi affine varieties which are not affine, alright, and then the what I am going to do is to tell you about more general varieties which are called projective varieties and open subsets of such projective varieties which are called quasi projective varieties, okay. Then our definition of variety will include affine, quasi affine, projective and quasi projective, okay, and these projective varieties are a completely different class of specimens, okay, whose properties are very different from the properties of affine varieties, okay. But to tell you where they come from, I just want to tell you that they come from the process of gluing, okay. So let me give you some motivation. So you see, let's look at the usual topology, okay, let's look at the usual topology and look at for example look at the complex plane or the real plane, alright, and so you know, let's do the following thing. We take the usual plane, and then suppose I draw the sphere here, okay, so here is my sphere. So this is a unit sphere in 3 space, okay, and assume that you are in R3, okay, assume you are in R3, and what you do is you have this is the origin, this is the point 1 comma 1 comma 0, okay, and or rather 1 comma 0 comma 0, and you know, so what I do is if I call this point as the north pole and if I call this point as the south pole, okay, you would have heard of the so called stereographic projection, in complex analysis, which identifies. So if I call this sphere as S2, so S2 minus the north pole can be identified homeomorphically with R2, okay, by projecting from the north pole, and S2 minus the south pole can be identified homeomorphically with R2 by projecting from the south pole, okay. So these are the so called Riemann stereographic projections from the Riemann sphere, okay, to the plane, and therefore the sphere minus the north pole is compactified. The 1 point compactification of the sphere minus the north pole is a sphere, and that corresponds to that will correspond to the extended plane by adding a point at infinity under this homeomorphism. So what it tells you is that the real plane has a 1 point compactification which is just the sphere, and so there are these two stereographic projections. Now what you must understand is that if you consider each of these things, they are you can call them as two open subsets of the sphere. Both are open subsets of the sphere, okay, and they cover the sphere, and each open subset looks like R2, because looks like R2 means it is a homeomorphic to R2 and the homeomorphism is via the stereographic projection. So what has happened is, so what we say is this is a standard example of what is called as gluing. So what you do is you take two copies of the plane, okay, and you glue them together, okay. So basically you take a copy of the plane and then you fold it to get the sphere minus the north pole, take the other copy of the plane, fold it to get the sphere minus the south pole, and just glue them together and you get the sphere, okay. Now this is a standard procedure. You have some spaces, you glue them together to produce new spaces, but the point is when you do this, the new space that you get will have completely new properties. So for example, in this case if you take the sphere, the new topological property that you get is that it is compact, whereas neither of the two copies that you originally started with to glue to get the sphere is compact. Of course both R2s are both copies of the plane are non-compact, because in Euclidean space something is compact, a subset is compact if and only if it is both closed and bounded with respect to the usual topology. So the moral of the story is that actually you are able to, by gluing spaces you are getting spaces with new properties, okay, and so this gluing process is the process that is used to produce new spaces from old spaces, alright. And basically another good example of gluing is, well, there are several examples. For example, I can take so I can just take I can take the complex, I can take the plane, okay, and thinking of this as a complex plane, let me say something. If you glue it correctly, okay, then you can make sense, instead of thinking of S2 as just the real sphere, you can think of S2 as a surface on which you can do complex analysis. You can make it into a Riemann surface, okay, and you can make sense of holomorphic functions, and then Liouville's theorem will tell you that there are no global holomorphic functions. It will tell you that every global holomorphic function will be constant. So the beautiful thing is that on the plane you will have so many holomorphic functions, okay, you have so many entire functions, whereas this glued object there are no entire functions. The only entire functions, namely the functions that are holomorphic everywhere, are constant. And so you are basically having two affine spaces, you have glued them together to get this space, and this space is compact and it has no global non-constant functions, okay. The same thing happens in algebraic geometry. A projective space is gotten by gluing a bunch of affine spaces, okay, and on the projective space you will see that there are no global regular functions. The only global regular functions on the projective space will be constants, okay, and it is a complete analogy to what is happening here. So it is a gluing process. So projective spaces are gotten by gluing affine spaces, okay, just like the sphere is gotten by gluing two copies of R2, alright. Of course some other examples of gluing are, for example, if you take a horizontal strip or a vertical strip for that matter, and then if you or for that matter well, if you glue the top edge and the bottom edge, what will happen is that you will get a cylinder, and that is by identifying the top edge and the bottom edge. You cut the strip, and then you identify the top edge of the strip with the bottom edge of the strip and fold it out, you will get a cylinder, you will get an infinite cylinder. Now the original strip is topologically different from the cylinder because the original strip is simply connected. Any simple closed curve in that original strip can be completely shrunk to a point, whereas the cylinder is not simply connected because any loop that goes around the cylinder that cannot be continuously shrunk to a point. So you see again you have produced by a gluing process you have produced a new topological space with topological properties that are very different from the properties of the original space, alright. Another example is of course you could have taken you could have done also something like this. You could have taken just a parallelogram, okay, and then you could have glued the parallel opposing edges, and the result is that you will get a torus, because if you glue the upper edge with the lower edge you will get a cylinder with two circles on the two ends which need to be further identified. If you identify them you will get a torus, and the beautiful thing is that this is simply connected but this is not, okay. So the gluing process is a very standard process. It is a process that allows you to produce new spaces with new with new properties, okay, and you must think of projective space also as coming out of a gluing process, okay. So I will explain how projective n dimensional complex space is gotten by gluing n+1 copies of n dimensional affine space, okay. And on what we are going to do is that we are going to define a Zariski topology on the projective space, okay. So we are going to define algebraic sets, we are going to define irreducible sets, we are going to define closed subsets of projective space, call them projective varieties, and then whatever we did for affine varieties lot of similar results like the Nullstellan sets etc. will also work for the projective case, okay. But of course certain things will go wrong, alright, and I will explain in the coming lectures, in this and the coming lectures, what is going to go wrong and what is not going to go wrong. So let me start with the definition of projective space. So PNC, so this is complex projective n dimensional space. Here is complex projective n dimensional space, and how is it defined? It is the space of lines in affine space. So complex projective n dimensional space is a space of lines in an+1, okay, and through the origin, and that is true not only for complex numbers, for any field. And how do I get it as a space? The reason I have to consider lines in n+1 space is because you see I want an n dimensional object, okay, and if I take lines in n space, okay, by taking lines I am cutting down by one dimension, so the resulting space will be n-1 dimensional. So if I take space of lines in n space I will get an n-1 dimensional space, okay, because I am actually modding out by scalars. So if I want an n dimensional projective space I should take lines in n+1 space, okay. So so how does one get it? One takes points in an+1 and then you go modulo an equivalence relation. What is the equivalence relation? The equivalence relation is very simple. So if you give me a point λ1 etc λn, okay, then that point defines the same line as some other point if and only if the 2 points have coordinates which differ by a non-zero constant multiple, okay. So if I take a point λ1 λn, so I will call them as λ0 to λn, right. So I am in an+1, so the coordinates are n+1 coordinates which I am not labeling the coordinates 1 through n+1, I am labeling them from 0 through n, which is the standard convention whenever you do studying projective space. So the line passing through this point, so this is the line passing through the point λ1 λ0 λn, this is the line passing through that, and this is what I am going to do. I am going to take this point λ0 lambda n, I am simply going to map it to the line passing through lambda 0 lambda n, and of course through the origin. That is the line that joins the point, this point to the origin. I am simply mapping this point to that line, okay. And what I want you to understand is that this is an equivalence relation in the sense that if you take this L lambda 0 lambda n is the same as L mu 0 etc mu n, that means both these points lie on the same line, and you know both these points lie on the same line if and only if this is a non-zero multiple of that by a single scalar, non-zero scalar, okay. So this is if and only if there exists t a non-zero element of the field such that mu I is equal to t lambda I for every I, okay. So you know between n plus 1 tuples of points you put this equivalence relation. This is an equivalence relation that 2 points, one point is a multiple of the other point by a non-zero element of the field, okay. That is an equivalence relation, and if you go modulo that equivalence relation, what you are going to get is precisely the projective space, which is a space of lines, okay. 2 points here, if they are equivalent, namely they will differ by their coordinates differ by one and the same scalar non-zero scalar multiple if and only if the lines that they define through the origin are the same, okay. So the space of, so what has happened is that we have gotten the projective space as a quotient, okay. It is a set modulo an equivalence relation, so it is a quotient, and this is very good because once you have this, for example if I have a topology here, I can transport the topology here by giving this the quotient topology, alright. So it is always good that whenever you have a quotient kind of situation, then you can transport from the source a lot of things to the target, right. So well you know I have the Zariski topology on this because this is after all sitting inside a n plus 1, which has a Zariski topology. This is affine n plus 1 space, and therefore this has a Zariski topology, and I can put the quotient topology on this, and that will give me a Zariski topology on Pn, alright. And in fact it will happen that this map is this map will be in fact even an open map, okay, and it will be of course continuous for the Zariski topology, alright. But then there is another way of defining the Zariski topology on this in a very in a slightly analogous way to the definition of the Zariski topology on affine space. So you see, so the point I want to make is that you know of course I for example you know I could have put k equal to, forget k being algebraically closed, I could have taken k to be real numbers, and then I will get real projective space, okay. And then I can study things on this. I can simply take the usual topology on top and then you know give this the quotient topology, alright. I could have done that, and similarly I could instead of k I can take complex numbers, and then I will get complex projective space, and on the complex projective space I could have again put the usual topology. I have the usual topology here, I could have given the quotient topology, okay. And because complex numbers is also an algebraically closed field, I have another topology here which is the Zariski topology, that also I can use to give a quotient topology here. So complex projective space has two topologies. One is the topology which comes as a quotient topology for the usual topology, and the other topology comes as a quotient topology for the Zariski topology on this punctured affine space above, okay. So now let me go back to how we define the Zariski topology on a n plus 1. See, the Zariski topology on affine space was defined by giving closed sets, and the closed sets were given as zero sets of I mean common zero loci of a bunch of polynomials, okay. Now what we are going to do is we are going to imitate the same thing here. What we are going to do is we are going to look at common zero loci of a bunch of homogeneous polynomials, okay. And then you see it will make sense. You see, if you take a polynomial function for a polynomial function, of course if you take a polynomial in n+1 variables, if I evaluate that polynomial on a line, alright, of course the polynomial, the values will change, okay, but if the polynomial is homogeneous, the property of it vanishing or not will not change, okay. So this is the first observation. If f of x0 xn is a homogeneous polynomial, okay, say homogeneous of degree d, then either f restricted to line through lambda naught lambda n is identically 0 or otherwise. Okay, so what I am trying to say is, because this is because you see f of lambda naught lambda n, suppose I put t lambda naught etc t lambda n is t power d f of lambda naught etc lambda n for t non-zero constant. So you know, if the polynomial vanishes at one point of the line, then it will vanish at every point of the line, okay. So in other words, so I can make sense of whether a polynomial vanishes on a line or not. But what is a line? A line is a point here, so I can make sense of whether a polynomial vanishes at a point here or not, okay, and then I define the closed sets here to be common zero loci of the bunch of points where the polynomials vanish, where all those points where a bunch of homogeneous polynomials vanish, okay. So what you do, in other words, it makes sense to look at the zero set of f in Pn. Okay, what is the zero set of f in Pn? Point in Pn where f does not vanish corresponds to a line on which f does not vanish. Point in Pn where f vanishes corresponds to a line on which f vanishes, okay. So let me repeat, I can make sense of the zero set of a polynomial in projective space, namely it is all those lines on which f vanishes, it is all those lines on which f vanishes, and I do not have to just do it for one polynomial, I can do it for any collection of polynomials. So what you do is, more generally we may define a projective algebraic set in Pn to be the common zero locus of a subset of homogeneous polynomials in k x0 etc xn, okay. And the fact is that we get a topology on projective space, that topology will be the so-called Zariski topology, okay. You can check that this gives a check that we get a topology called the Zariski topology on projective space by taking closed sets to be projective algebraic sets. Okay, if you take projective algebraic sets to be closed sets, you get a topology on projective space, and that is called the Zariski topology. And the fact is that the fact is the following: the fact is that that topology is the same as the quotient topology that you get from the Zariski topology on top. Okay, this topology is the same check also that this topology is the same as the quotient topology for pi. I will call this map as pi, the projection using quotient topology for pi from the Zariski topology on a n plus 1. Okay. So the moral of the story is that you can get a Zariski topology, you can get a topology on this, a Zariski topology on this, that can be done in two ways. Either you take the quotient topology, I mean it is a topology that you put that makes this map continuous, okay, and that is one definition. Okay, the other definition is that you define the topology directly on this to be given by closed sets which are given by common 0 loci of a bunch of homogeneous polynomials. The only difference with the projective case and the affine case is that in the affine case you consider all polynomials, but in the projective space, in the projective case you consider only homogeneous polynomials. And you know why you have to consider homogeneous polynomials, because only for a homogeneous polynomial you can say for sure whether it will vanish uniformly on a line passing through the origin. Okay, if it is a non-homogeneous polynomial, it could vanish at some points on the line and it could be non-vanishing at other points on the line. Okay, if you take a non-homogeneous polynomial and take its 0 set, that 0 set will be a hypersurface, okay, which will be n dimensional in n plus 1 space, and that hypersurface could hit the line at not at all points, it need not contain the line. So it could hit the line at some points and it could not hit the line at some points. So a non-homogeneous polynomial could vanish at some points on the line and not vanish at some other points of the line. But if you have a homogeneous polynomial, it either completely vanishes on the line or it vanishes at no point on the line. Okay, so if you take a homogeneous polynomial, it is very easy to define the 0 set of that in projective space, and then if you take a bunch of homogeneous polynomials, then the common 0 locus of this bunch of homogeneous polynomials is what is called an algebraic set, and that is how a closed set is defined. Okay, and this gives you the Zariski topology on the projective space. And now you know a lot of statements that we know for the usual affine space, the same statements will carry over for projective space. The only thing is, for example, in the affine case you deal with ideals, general ideals and general polynomials. In the projective space you will deal only with homogeneous polynomials, and you will deal with ideals which are generated by homogeneous polynomials, and these are special, they are called homogeneous ideals. Okay, so just as in the affine case you have a bijection between radical ideals and algebraic subsets, in the projective case also you will have a bijection between radical homogeneous ideals of this this ring, polynomial ring in n+1 variables, and projective algebraic subsets, but you will have to throw out one ideal which is called the irrelevant maximal ideal, and that is the ideal generated by all the variables. That is the one that you have to throw out, and you have to throw it out because on top you have thrown out the zero of the zero set of that which is the origin. Okay, you have to throw that out. Okay, so and just like in the affine case where you have the affine Nullstellensatz, which says that if you take an ideal which is you know a proper ideal, then the zero set is non-empty. Similarly, you will also see here that if you take a homogeneous ideal which is not which is essentially not, whose radical is not the irrelevant maximal ideal, then its zero set will be non-empty. So you get a projective version of the Nullstellensatz. So lots of this correspondence between ideals and closed subsets that you had for affine space will also hold for projective space, and we will review that in the next lecture. But there is one point of caution. The point of caution is the following: you can go and start defining regular functions on a projective variety, okay, on an open subset of a projective variety. We will call an irreducible closed subset of Pn as a projective variety, alright, and it will turn out that it will be a closed subset will be irreducible if and only if its ideal is prime. The ideal will be a homogeneous ideal, but you will require that it has to be prime. And what will happen is, of course, that you know in the projective case also, if you look at so in the projective case also you can define regular functions. The only thing is that in the affine case your regular functions were quotients of polynomials, okay. Now you have to define them as quotients of homogeneous polynomials, okay. If you take quotients of two homogeneous polynomials and assume that both polynomials are homogeneous of the same degree, then that will define a proper function on affine on the projective space, because you know if I divide two such polynomials, then the t power d's, and if they have the same degrees, the t power d's will get cancelled, and therefore a quotient of homogeneous polynomials of the same degree will define a nice function on the projective space. Functions that look locally like this will be called regular functions on the projective space. And then the beautiful thing is that if you try to look at any global regular function on projective space, it will turn out to be constant, just like if you try to look at a global holomorphic function on the Riemann sphere, it has to be constant, okay. So this projective and it is true for any projective variety. If you look at any global regular function, it will be a constant. We will prove that, okay. And this is in sharp contrast with the case of affine variety, when the global regular functions are given by all the polynomials restricted to that affine variety, and there are so many of them, whereas if you go to projective varieties there are no non-constant regular functions, okay. So and of course I also forgot to tell you, just like in this case S2 is a union of two R2s, I will show in the next class that Pn is a union of n+1 copies of An. So the projective space locally it is covered by n+1 open sets. Each open set looks like An, affine n space. So what you have done is you have taken n+1 copies of affine n space and glued them in a nice way to produce the projective space. And the beautiful thing is that though each of the pieces that you glued with have lots of regular functions, polynomials, on this glued object there is no global regular function which is not constant, okay. So we will see all these aspects in the forthcoming lectures. And let me also tell you one more point of difference, that is that for an affine variety the coordinate ring of the affine variety is an invariant, namely two affine varieties are isomorphic if and only if their coordinate rings are isomorphic, and now this is completely going to be false for projective varieties, okay. So the same projective variety can be embedded into different projective spaces, and if you try to define the ring of functions on that as this polynomial ring modulo the ideal, the homogeneous ideal, you will see that that ring is capable of changing. So the embedding of a projective variety in some projective space could be very different, I mean, alright. So you do not have the beautiful analog of coordinate ring for affine varieties, you do not have the correct analog in that sense for projective varieties, okay. And for that matter that is what leads one to study line bundles and sections of line bundles etc. on projective varieties, which are probably the content of a second course in algebraic geometry, okay. But I will stop here and we will continue in the next lecture.